Time looks continuous to you for the same reason a movie looks continuous on a screen. 24 separate still frames flash in front of your eyes every second, and somewhere between the screen and your brain, the gaps get sealed shut. You never see the cuts, you only see motion. Nobody questions this about film, because the trick is well understood. A projector, a frame rate, a brain doing the stitching. What almost nobody asks is whether reality is doing something similar to you right now, feeding you a string of separate moments and quietly hiding the seams. A handful of physics results from the last few years are the first real hint that the seams might exist, and almost nobody outside a physics department has heard of them. Try naming the very next real number after 0. Whole numbers do not count here. You need the kind of number we use for any precise measurement, including time. Say 0.1. There is 0.01, waiting between your answer and 0. Say 0.01, and 0.001 is waiting between that and 0. You can cut the gap in half forever, and there will always be a number sitting inside the half. There is no next real number after 0. We have not simply failed to find it. The structure of the real number line guarantees it can never exist. Between any two numbers, no matter how close together, there is always room for another one. That single property is the actual mathematical definition of a continuum. No smallest gap, no next step. It is a precise, testable structure, and it is the exact structure we decided, back in the 1660s, that time is built from. You might think that sounds like a property of numbers, not of time itself. Numbers are a label, and time is the thing being labeled. Fair point. Except we do not use real numbers to label time the way a sticker labels a box. We build the laws of motion directly out of the assumption that time has that property inside the working machinery of the equations. Every law we use to describe how anything moves, how fast a planet falls, how a current builds in a wire, how a quantum state shifts from one instant to the next, is built from something called a derivative. A derivative answers one question: how much does a quantity change, divided by how much time that change took, as the time interval gets smaller and smaller, with no limit on how small. The interval has to actually vanish, not just shrink down to something tiny and stop. You take a smaller slice, then a smaller slice than that, forever. And the equation only works if you never hit a bottom. Quantum mechanics and general relativity agree on almost nothing. One describes particles as probability spread across space. The other describes gravity as the bending of space itself. We cannot currently write them as a single theory, and for a century we have tried and failed to merge them. But both of them, without exception, lean on the same derivative, the same vanishing time interval, the same assumption that you can always slice a moment thinner. It may be the only thing the two deepest theories physics has ever produced have fully agreed on. Isaac Newton built this method around 1665, while Cambridge sat closed for plague, and he worked alone from his mother's farmhouse. He was uneasy enough about it that he tried to dress the idea up differently, calling it the ratio of quantities at the exact instant they vanish, a phrase built specifically to dodge the criticism waiting for it. Gottfried Wilhelm Leibniz built a version of the same method about a decade later, independently, in Germany, calling the vanishing quantities infinitesimals outright, and the notation he invented is the notation we still write on chalkboards today. Neither man could fully explain why we were allowed to do this. They were dividing by quantities they themselves called infinitely small, smaller than any number you could name, yet somehow not 0. That did not sit well with everyone. Decades later, the philosopher George Berkeley spent an entire essay arguing that these vanishing quantities were neither finite quantities nor strictly nothing, and that we had built an enormous structure on top of a gap nobody had actually closed. He was right about the gap. He was wrong about the consequence. The technique kept working. It predicted the tides. It plotted the orbits of moons nobody had seen yet. It eventually steered a spacecraft onto the surface of another world. So we patched the gap, then rebuilt it on firmer ground roughly 2 centuries later, using a more careful definition of what it even means for a quantity to vanish. But notice what we never questioned in any of that repair work. Not once, in 3.5 centuries, did we go back and ask whether time itself actually has the property we assumed it had from day one. We fixed the logic. We never tested the physics. You might point out that our predictions land to a dozen decimal places and ask how an assumption that wrong could possibly produce results that right. The answer does not flatter the assumption. Treat a crowd of people as a flowing liquid, and you can predict exactly how it will move through a stadium exit, how fast, in what pattern, down to a level that looks like magic. The equations for that prediction never once mention an individual person. They treat the crowd as continuous, smooth, infinitely divisible, and they work beautifully right up until you stand close enough to see that the crowd is actually built from a few thousand separate, countable bodies. Precision at one scale tells you nothing about texture at a smaller one. Every test of relativity and every test of quantum mechanics that has ever been run has also been a test performed from a comfortable distance, at scales enormously larger than where any graininess would first show up. We may be doing exactly what the stadium equations do, getting every prediction right while standing too far back to see whether the thing we are predicting is actually built from discrete pieces underneath. Picture 2 clocks side by side. One has a hand that sweeps, smooth, no visible steps, the kind you would call continuous just by watching it. The other has a digital display that jumps, 1 whole second appearing and disappearing with nothing shown in between. Both clocks sit in the same room, measuring the exact same flow of seconds. Only one of them is telling you the truth about what that flow actually looks like underneath. The honest question, the one none of us could answer for 350 years, is which one? And if it turns out to be the second hand, every equation built on the assumption of endless slicing would need a different kind of mathematics entirely, one built from steps instead of slopes, the way a staircase replaces a ramp. What stays with me about this is not that the assumption might turn out to be wrong. It is that this exact mathematics went on to predict the tides, plan the orbits of unseen moons, and steer a machine onto the surface of another world. And across all that success, none of us went back to check the one claim sitting underneath all of it. That a moment can always be cut smaller, forever, no bottom. If time does have a smallest gap somewhere, a true next moment the way integers have a next number, then every derivative on the books today is quietly, technically incomplete at some scale, too small for any experiment we have built so far to notice. So the question is not whether the mathematics works. It clearly does. The question we are left with is whether anything in nature is required to obey a limit on how small a step it is allowed to take. Nature enforces a speed limit on change, and it has nothing to do with how small a step time is allowed to take. This limit shows up even when nothing moves through space at all. A single atom sitting still inside a trap, shifting from one internal state into a completely different one, is still bound by it. We are talking about a state turning into another state, not an object crossing a distance. The first thing people confuse this with is the speed of light. It has nothing to do with it. The speed of light caps how fast something can travel from here to there. This caps how fast something can stop being itself and become something completely different, with no travel involved at all. Picture the energy inside any quantum system as a set of hands turning on a hidden clock face. One hand for every distinct energy the system carries. each one rotating at its own speed. A system in a single, simple state changes very little. A system built from many different energies at once watches its hands spin apart from each other. And once those hands have rotated far enough to no longer line up with where they started, the system has become something measurably new. Higher energy means a faster hand. Faster hands mean the pattern scrambles into something new sooner. That is the entire mechanism, and it is also the entire limit. Low energy buys you slow hands. There is no way around that exchange. We need to talk about the floor those hands are measured from, because it is stranger than it sounds. Every quantum system has a lowest possible energy it can ever hold, and even sitting at that floor, the system is never perfectly still. The same uncertainty that keeps you from pinning down a particle's exact position and exact speed at the same moment also forbids a system from having both zero energy and zero motion at once. There is always a small leftover jitter sitting at the very bottom, a minimum hum that can never be switched off. You can watch this hum win an argument with an entire branch of chemistry. Cool ordinary helium down far enough and the laws of pressure and temperature say it should freeze solid, the way every other element does. It refuses. Under normal pressure, helium stays liquid all the way down to absolute zero, because the floor energy it is never allowed to drop below keeps every atom jittering just enough to prevent the orderly lattice a solid requires. We are looking at a real liquid, sitting in a real container, kept that way by a limit most people have never heard of. None of us tend to picture stillness as something that costs anything. We treat rest as the default, the cheapest state there is, the place everything settles into once nothing is pushing on it anymore. Nature does not agree. Perfect rest is not free, and it is not even allowed. Something always has to keep moving, even at the very bottom, and that leftover motion is the only reason anything is ever permitted to change at all. That floor is the baseline every speed limit gets measured against. Energy above the floor is what buys you speed. No floor energy to spare, no purchase, no change. Werner Heisenberg noticed a rough version of this trade-off back in 1927, tucked inside the same work that gave us his uncertainty principle, though he never turned it into a hard rule. It took until 1945 for two physicists working in the Soviet Union, Leonid Mandelstam and Igor Tamm, to convert that rough intuition into an actual bound. They proved that a quantum state needs a minimum real amount of time to evolve into something fully and measurably different from where it started, and that minimum time depends on how spread out the system's energy is across all those rotating hands. We got a second, independent bound more than 50 years later. In 1998, Norman Margolis and Lev Levitin found a different limit, one that does not care how spread out the energy is, only how much energy the system carries above its floor. Their bound and the older one do not always agree on which is stricter, and for decades, nobody had actually watched both operate on the same system to see which one wins. For an object holding the kind of energy your body holds, warm, large, packed with motion, this bound predicts speeds so fast they cap out at lengths of time too small to ever matter in daily life. You will never bump into it making a decision or lifting a hand. It only becomes a real, binding constraint once a system has been cooled down close to its floor on purpose, stripped of nearly all its spare energy. That is exactly the kind of system physicists have spent the last few decades learning to build, in a freezer colder than empty space. Neither bound is measuring a small wobble. Both are measuring the time it takes a system to become something a detector could never mistake for where it started. The quantum version of a coin landing fully on heads instead of spinning halfway between faces. A system can drift a little and still be recognizably itself. These limits only switch on once the system has fully become something else, end to end. In 2021, somebody finally checked which bound actually wins. A single experiment tracked both limits acting on the same evolving quantum system. and found exactly what the underlying math predicted: two separate regimes sitting back to back. Early in the evolution, the older bound was the one holding things back. Later, in the same evolution, control quietly passed to the newer one. Two different limits, both real, taking turns running the same clock. A result like that tends to stay locked inside a physics journal, and mostly it has. But look at what it actually says. Change itself, the simple fact of a system becoming something else, has a price. And the price is paid in energy, not in effort, not in time alone, and not in anything you can will into happening faster. This is not limited to exotic lab systems built to test the bound on purpose. It applies to every arrangement of energy that exists, which includes you, which includes the very specific arrangement of energy keeping your heart on its current beat and your neurons mid-signal right now. Nobody has measured how close any part of you sits to this particular ceiling. Nobody needs to, for the limit to still apply. What nobody has ever shown us is a single physical system, something you could point to and not just calculate, sitting right up against this limit on purpose, ticking as fast as the laws of physics will allow and not one fraction faster. It exists, and on the right kind of cold day, you could hold it. Start with the ordinary version of a crystal, the kind sitting in your kitchen as salt. Inside that crystal, atoms repeat at a fixed spacing, the same gap appearing again and again as you move through the structure. Slide over by that exact distance and the arrangement looks identical to where you started. Slide by anything less, and it does not. Space, inside a crystal, has a rhythm to it, a repeating beat written into the positions of atoms instead of into sound. Nothing in the laws governing those atoms demands that particular spacing. The same physics would have been satisfied with a different gap, a different arrangement entirely, or no order at all, the way a liquid has no fixed spacing anywhere inside it. The crystal picks one specific rhythm out of every rhythm the laws would have allowed, and once it picks, it commits, completely, everywhere inside the structure at once. We call that choice spontaneous, because nothing forced it. It happened anyway. A magnet makes the same kind of choice. Heat a piece of iron past a certain temperature, and every atom inside it points its own tiny magnetic moment in essentially a random direction, the whole block magnetically blank. Cool it back down, and at some point every atom commits to pointing the same way, with no individual atom forced into it by laws that have no preference for north over south. The material decides, together, all at once, and stays decided. Frank Wilczek asked an odd question about that kind of choice in 2012. If space can spontaneously organize itself into a repeating beat this way, could time do the same? Not a clock counting time from the outside, but matter whose natural lowest energy behavior repeats on its own schedule, the way the salt crystal repeats its own spacing, without anything from outside forcing the rhythm. You can hear how that sounds like it should be cheating. A pattern that repeats forever, on its own, sounds uncomfortably close to a machine that runs without fuel. We noticed the same thing almost immediately, and within a couple of years, a formal proof closed off the most radical version of the idea. A system sitting in true equilibrium, completely settled, with nothing flowing in or out, can never tick on its own. That door shut fast, and for good reason. Energy still has to balance. But a second door stayed open, and it led somewhere stranger than the first idea did. Instead of a crystal ticking with nothing driving it, take a system you are already pushing rhythmically from outside, on purpose, the way you would tap a drum at a steady beat. An ordinary material struck this way matches your beat exactly. Tap it twice a second, and it responds twice a second. There is no reason to expect anything else, and for almost every material that exists, nothing else ever happens. In 2016 and 2017, We finally built materials that broke that expectation anyway, in two labs working independently of each other. One used a chain of charged atoms held in place by electric fields built at the University of Maryland. The other used flaws inside a diamond, individual defects in the crystal lattice built at Harvard. We drove both systems with the same kind of steady external tapping, and in both, the matter refused to follow along one-to-one. Tap it twice a second, and it answered once a second, locking onto exactly half the rhythm you gave it. The locking is the part that separates this from an ordinary pushed system, like a swing that happens to settle into a slower sway. Detune an ordinary swing even slightly, and the slower sway falls apart immediately, because nothing is holding it there except a lucky coincidence of timing. Detune the tapping on these materials. Push the beat slightly faster or slower than before, and the half-rate response stays locked exactly where it was, refusing to drift even a little. That stubbornness is what tells you this is not a coincidence of timing. It is a real, stable phase of matter, the same way ice is a stable phase of water and not a coincidence of cold. The material has organized its own internal motion into a period the driving force does not contain on its own. The same way the salt crystal organizes atoms into a spacing that empty space does not contain on its own. Matter, structured this way, is doing in time exactly what an ordinary crystal does in space, breaking a smooth, unmarked background into a fixed, repeating beat. We call the result a time crystal because there is no more honest name for it. None of this needed exotic new physics. We needed cold, the same kind of cold that keeps liquid helium running right past its own freezing point instead of turning solid. Both labs worked with systems pushed down near their lowest possible energy, stripped of nearly all spare motion, exactly the regime where a speed limit on change stops being invisible and starts being something you can actually measure against a clock on the wall. We have read the mechanism behind this more than once, traced the math, watched it check out every time, and it still does not fully stop feeling like it should not be allowed. Knowing exactly why a half-beat locks in does not make the half-beat feel less like a small rebellion against the thing driving it. That gap between understanding something completely and it ceasing to feel strange is its own kind of result, and nobody has explained that part yet either. A few grams of matter, sitting in a lab built specifically to keep it that cold, is doing something no clock built by a watchmaker has ever done. It is keeping its own time, from the inside, against the rhythm of whatever is pushing on it from the outside. The next moment, the one mathematics insisted could never exist, with no smallest gap between it and the moment before, now has a real, physical counterexample sitting in a lab. If something built from ordinary atoms can organize itself into a discrete, repeating beat the moment you get it cold and isolated enough, the question worth carrying forward is what happens at the opposite extreme, inside something warm, crowded, and never isolated from anything, the way every living body on this planet has always been. A neuron does not have a way to fire a little. Either it crosses a threshold and sends a full, complete electrical spike down its length, or it stays silent and sends nothing at all. There is no quieter version of a spike, no half signal, no gentle taper between firing and not firing. Physiologists found this out by stimulating single nerve fibers with currents of carefully varied strength, expecting the response to scale smoothly with the input, the way turning a dial up gradually raises the volume on a speaker. It does not work that way. Push the stimulus just past the threshold and you get the exact same spike you would get from a much stronger push. The nerve has only one move available to it, full or nothing. And physiologists in the early 20th century, including Edgar Adrian, who spent years recording single fibers with instruments sensitive enough to catch one impulse at a time, gave this behavior a name that has stuck ever since. We call it the all or none principle because those are actually the only two options on offer. A spike is not a wave rolling smoothly along a wire. It is closer to a single struck note, complete the instant it happens, with nothing partial about it anywhere along the way. The reason it works this way comes down to a runaway feedback loop built into the cell membrane itself. Once enough sodium channels along that membrane pop open, the rush of charged sodium ions flooding in makes the local voltage shift even further in the direction that opens more sodium channels, which lets in more sodium, which opens still more channels. Cross the threshold, and that loop takes over completely, racing to its maximum on its own, with no way to stop partway through once it has started. Stay below the threshold, and the loop never engages at all, and nothing happens. There is no stable middle setting for a mechanism built like that. It either catches fire or it does not. What happens immediately afterward matters just as much as the spike itself. For a brief window afterward, somewhere around 1 to 2 thousandths of a second, that same patch of nerve cannot fire again no matter how hard you push it. The channels that let the spike happen are still resetting, locked shut, completely unavailable. Physiologists call this the absolute refractory period, and the name undersells how strict it is. It is not that a second spike becomes unlikely. It becomes, for that brief window, physically impossible. Then the lock releases, and firing becomes possible again, gradually at first, and then fully. Mathematics insists there is no such thing as a true next moment, no smallest gap between one instant and another, because you can always find a smaller one. A neuron does not agree. A neuron has an actual smallest gap built into it, a real minimum interval between one tick and the next one, enforced not by philosophy but by the physical reopening of a channel. We are not speculating about whether something in nature might have a true next step. We are looking directly at one, sitting inside your skull right now, doing exactly that, over and over, every time any thought you have ever had moved from one neuron to the next. Your heart runs on the same kind of discreteness, at a slower, heavier pace you can actually feel. A small cluster of specialized cells near the top of your heart, called the sinoatrial node, generates an electrical discharge on its own, with no outside signal telling it to. That discharge does not arrive as a continuous current humming through the muscle. It arrives as a discrete event, a single countable pulse, somewhere between 60 and 100 times each minute while you are at rest. Each pulse spreads outward and triggers the upper chambers of your heart to contract, then reaches a second relay point called the atrioventricular node, where something deliberate happens that has nothing to do with limits or accidents. That second node holds the signal for about 1/10 of a second before letting it continue on to the lower chambers. That pause is not a flaw in the wiring. It is required. Without it, the upper and lower chambers would contract together instead of in sequence, and the heart would lose most of its ability to actually move blood. Evolution built a deliberate, measured gap into the timing of your own heartbeat, because the alternative, a smooth and continuous signal with no discrete delay anywhere in it, would pump blood badly. The discreteness is not incidental to how your heart works. It is the entire reason your heart works at all. Put your attention on your own pulse for a moment, if you can feel it without trying too hard. What you are feeling is not a flow. It is a sequence, a count, one discrete electrical event after another, each one separated from the last by a real, physical, non-negotiable interval, the same kind of true next step a neuron has and a continuous mathematical line never could. There is a slower clock running underneath all of this, one that takes roughly 24 hours to complete a single cycle, and it is built from the same kind of discrete machinery, just stretched out over a much longer interval. Inside nearly every one of your cells, a small set of genes and the proteins they produce are running a loop. Two of the central players are usually called period and cryptochrome. Their proteins accumulate slowly through the day, build up enough to block the very genes that made them, get broken down over several hours once they have done that blocking, and then let the whole cycle start again from nothing. One full loop takes close to a day, not because any cell is counting hours, but because the chemistry of building up, blocking, and breaking down those specific proteins simply takes that long to complete. The clock is not measuring time from outside the cell. It is made of time, built directly out of a sequence of discrete molecular events with nothing continuous connecting one stage to the next. We learned the shape of that loop largely through a genetic puzzle, identified in fruit flies by Ronald Konopka and Seymour Benzer in the early 1970s, then worked out at the molecular level over the following 2 decades by Jeffrey Hall, Michael Rosbash, and Michael Young, work recognized with the Nobel Prize in 2017. Almost every cell in your body runs a version of this loop on its own. Your liver, your skin, your heart muscle, each keeping its own local rhythm. We know the loop is actually internal and not just a reaction to sunrise and sunset because of what happens when every external time cue gets removed completely. In the 1960s, a French geologist named Michel Siffre spent extended stretches living alone inside caves, with no clocks, no daylight, and no way to know what time it was on the surface. His body kept running on a cycle close to 24 hours anyway, drifting slightly later day by day, with nothing outside him pushing it in that direction. Controlled laboratory versions of the same experiment, run later with proper monitoring equipment, found the same thing, an internal loop that free runs on its own schedule, usually a little longer than 24 hours, when nothing from outside is allowed to correct it. None of those local clocks would stay together for long without something synchronizing them, and the way your body solves that problem is stranger than most people ever learn. A small cluster of neurons sits just above where your optic nerves cross, and it receives light information from a set of light-sensitive cells in your retina that have nothing to do with seeing images. Those particular cells, identified by researchers including David Burson in the early 2000s, do not feed the part of your brain that builds pictures out of color and shape. They feed only this one cluster, reporting essentially a single number, how bright the room is right now. And that cluster uses the number to reset the chemical loop running in every other clock throughout your body, once a day, keeping thousands of separate, independently ticking cells from drifting apart. You are not underneath any of this, a smooth, continuous process that merely feels like it is divided into moments. You are a nested structure of discrete clocks, a fast one counting electrical spikes in thousandths of a second, a slightly slower one counting heartbeats once or twice a second, and a much slower one counting a single chemical loop that finishes roughly once a day, each layer built from real, physical, countable steps with actual gaps between them. If something built entirely from ordinary cells, sitting at body temperature, surrounded by trillions of other cells, never isolated and never cooled anywhere close to a laboratory's careful conditions, can still organize itself into discrete, countable ticking at 3 different scales at once, the question worth carrying forward is why the equations describing the universe those cells live inside have spent 3.5 centuries insisting on the opposite assumption. Every clock humans have ever trusted as uniform has eventually been caught lying by the next clock built to check it. The first clock we ever trusted was the sky itself. Watch the shadow on a sundial, and you are measuring the day the way every civilization measured it for most of human history. The sun crossing from one side of the sky to the other, a single rotation, 1 unit, repeated. It feels uniform. It is not. The length of a solar day actually changes across the year, sometimes by close to 30 seconds, because the Earth does not orbit the sun in a perfect circle and does not sit perfectly upright while it does it. Around December, the sun appears to move faster across the sky than it does around September. An hour measured by shadow in winter is not quite the same length as an hour measured by shadow in summer. For most of history, nobody could tell. At its worst, around early November, a sundial can sit nearly 16 minutes away from the smooth, idealized clock time you would check on your phone today, a gap large enough to make you late for something if you trusted the shadow completely. Two separate effects stack on top of each other to create that gap. The Earth moves faster through its orbit in January, when it sits closer to the Sun, and slower in July, when it sits farther away, the same way a planet has to speed up near the bottom of any elliptical path and slow down near the top. On top of that, the Earth's axis sits tilted rather than upright, which means the Sun's apparent eastward crawl against the background sky is not even across the year, even when the orbital speed alone is accounted for. Neither effect is a flaw in the Sun. Both are just consequences of orbital geometry that nobody built a precise enough shadow to notice until a steadier clock came along to compare it against. The sundial itself was not precise enough to catch its own mistake. The lie was sitting right there in the data the whole time, and the instrument measuring it was too blunt to read its own error. Christian Huygens changed that in 1656, building the first working pendulum clock, refining an observation about the steady rhythm of a swinging weight that Galileo Galilei had written about decades earlier without ever finishing a working version himself. A pendulum clock kept far better time than a shadow ever could, consistent hour after hour in a way the sky was not, and the moment it became good enough to compare directly against the Sun, it exposed the Sun as the unreliable one. Astronomers had to invent something called mean solar time, an artificial, average day built by smoothing out the Sun's real, lumpy schedule into a fictional, perfectly even one. The clock on your wall, even today, does not actually track the Sun. It tracks a polite mathematical fiction invented specifically because the real Sun could not be trusted to keep its own appointments. So the first fix for an unreliable clock was to stop trusting nature directly and build an idealized, smoothed version of it instead. That move should sound familiar. It is the same move physics has been making with time itself for 3.5 centuries, swapping a real, possibly uneven thing for a smooth mathematical stand-in, and then quietly forgetting that a substitution never happened. Mean solar time held up for nearly 3 centuries, treated as the closest thing to true, uniform time that human beings could access. Then, in 1927, Warren Marrison and Joseph Horton, working at Bell Telephone Laboratories, built the first clock driven by a vibrating quartz crystal instead of a swinging weight. Quartz holds a property called the piezoelectric effect, where squeezing or flexing the crystal generates a small electric voltage, and running a voltage through it in reverse makes the crystal flex. Wire that property into a circuit correctly, and the crystal vibrates at its own natural rate, on its own, tens of thousands of times every second, with a regularity that depends only on the precise geometry of the crystal itself, rather than on a swinging weight fighting against air resistance and friction. Once quartz clocks were running steadily for long enough, they caught the mean sun in the same kind of lie the pendulum had once caught the real sun in. The supposedly uniform, average day was not perfectly uniform either. The Earth's own rotation rate wobbles, slowing down gradually over centuries because the moon's pull drags on the oceans like a brake, and also drifting unpredictably over shorter stretches because molten rock shifting inside the planet very slightly changes how fast the whole sphere spins. Mean solar time had quietly inherited the imperfections of the very planet it was built to average out. We finally stepped outside the Earth entirely in 1955, when Louis Esson and Jack Perry, working at the National Physical Laboratory in Britain, built the first practical atomic clock, counting not a swinging weight or a vibrating crystal, but the natural oscillation of a cesium atom shifting between two energy states, a rhythm that has nothing to do with planets, oceans, or tides at all. By 1967, That oscillation had replaced the Earth completely as the official definition of a second. For the first time in the entire history of timekeeping, the standard for a uniform tick came from inside an atom instead of from watching something large move. That did not finally settle the matter. It just exposed a new victim. Once cesium clocks were precise enough to be trusted completely, the planet itself became the thing failing to keep time. Earth's rotation drifts in more ways than the long, slow breaking from the moon's pull on the oceans. Redistribute enough mass around the globe, the way a strong El Niño shifts huge volumes of warm water and shuffles the entire atmosphere's wind patterns, and the planet's spin measurably changes too, lengthening or shortening each day by a fraction of a thousandth of a second. The same way a spinning skater speeds up by pulling their arms in and slows by spreading them out. Earth's rotation, irregular and unpredictable at that level, no longer matched the atomic second closely enough to stay in sync, and every so often the gap grows large enough that an extra second has to be inserted into civil clocks worldwide just to drag our calendars back in line with how fast the planet happens to be spinning that particular year. We started correcting the planet to match our instruments instead of the other way around. That reversal is strange enough that it could not last forever either. The practice is now scheduled to be retired completely by the mid-2030s because modern computer networks find an unpredictable extra second dropped into the year harder to handle gracefully than almost anything else we ask them to track. There is something almost funny sitting underneath all 400 years of this, if you let yourself notice it. Civilizations set their clocks by the sun for thousands of years without a single complaint, right up until they built an instrument precise enough to catch the sun misbehaving. We have now reached the point where the planet itself needs periodic correction to keep up with machines built out of vibrating atoms. The thing being judged for unreliability keeps changing, the judgment itself, that whatever we are using as the reference right now is finally, truly uniform, has never once survived contact with the next instrument. Each upgrade did not just improve on the last one by a little. A good pendulum clock could be trusted to within a few seconds across an entire day. A good quartz crystal oscillator could hold that same drift down to a small fraction of a second across an entire year. A modern cesium atomic clock can run for longer than the age of the universe and lose less than a single second. Each generation of instrument did not refine the one before it. It made the one before it look almost careless by comparison. And in every single case, without one exception across 400 years, the new instrument's first real discovery was a flaw in whatever it had just replaced. Physics has been resting its entire mathematical foundation, the same one built on a moment that can always be sliced thinner, on the assumption that this pattern simply stops, that time itself is the one thing in this whole 400-year history that will never get caught by a finer instrument. Nobody has ever built a clock fine enough to test that assumption directly. If you wanted to be the first, the only honest question left is how fine an instrument would actually have to be before it could. Physics already has an answer to how fine an instrument would need to be, calculated decades before anyone had a reason to ask the question seriously. In 1899, a German physicist named Max Planck noticed something almost nobody else had thought to look for. Every unit you have ever used to measure anything, a second, a meter, a kilogram, was invented by some specific group of people, tied to something arbitrary. The length of a king's arm, the swing of a particular pendulum, the mass of a particular lump of metal sitting in a vault in France. None of those choices come from nature itself. A civilization on another planet, with no access to any of our kings or vaults or pendulums, would never independently arrive at a second the length we use. Planck wanted units that any civilization, anywhere, working from nothing but the constants built into the laws of physics, would eventually land on independently. He took three numbers that show up again and again throughout the deepest equations we have: the speed of light, the strength of gravity, and a constant tied to the smallest possible packet a quantum process can come in, and combined them mathematically until the result had units of time. The combination is forced. There is only one way to multiply and divide those three constants together, and end up with seconds instead of meters or kilograms. We call the result Planck time, and it does not belong to us any more than it would belong to anyone else who ever worked out the same three numbers. Each of those three constants is a signature, a fingerprint left behind by one specific theory. Wherever the speed of light shows up doing real work in an equation, relativity is involved. Wherever the gravitational constant shows up, gravity is involved. Wherever that quantum packet size shows up, quantum mechanics is involved. Planck time is the one scale in all of physics where every single one of those three fingerprints appears in the same equation at the same time, forced together, with none of them outweighing the other two. It is not an arbitrarily tiny number somebody happened to calculate. It is the specific point where all three of our deepest theories are mathematically required to speak at once, whether or not we currently know how to make them agree with each other. The value that combination produces is small in a way that breaks most ordinary language for small. It comes out to roughly 5 times 10 to the negative 44th power of a second. Stretch a single Planck time out until it becomes one full, ordinary second, the same length of time it takes you to blink. Now apply that exact same stretch, the identical multiplication, to a second sitting right next to it. That second does not become a minute. It does not become a year, or 1,000 years, or even the entire age of the universe. It becomes something on the order of 40 trillion times longer than the age of the universe, a number so far past anything you can picture that the only honest thing to do with it is notice that you cannot. We do have one more grounded way to feel the size of that gap, using the fastest events humans have ever actually managed to measure rather than pure arithmetic. Laser physicists have pushed their instruments down into the realm of zeptoseconds, trillionths of a billionth of a second, fast enough to catch a single photon crossing a hydrogen molecule mid-flight. That is, right now, the sharpest shutter speed our species has ever built for reality, and it still sits something like a trillion times above the Planck scale. Every instrument we have ever built, including our absolute best, has not even started approaching this number. We are not close. We are not in the neighborhood of being close. That same combination of constants produces a companion figure for distance instead of duration, called the Planck length, and the two are tied together in the simplest way possible. A Planck time is just the time it would take a beam of light to cross a single Planck length, the smallest interval of duration paired naturally with the smallest interval of space. Neither one was built to relate to the other. The relationship falls straight out of treating light's speed as fixed, the same constant doing the same job it does everywhere else in physics. A number that small is not a curiosity sitting in a textbook footnote. There is a real physical reason this particular combination of constants marks a meaningful boundary rather than an arbitrary one, and it comes from what happens when you try to concentrate enough energy into a small enough space to actually probe it. To examine anything smaller, you need to hit it with something carrying a shorter wavelength, and a shorter wavelength always costs more energy. The same reason an electron microscope can resolve detail an ordinary light microscope cannot by using electrons with far shorter wavelengths than visible light ever has. Push that logic far enough down toward the Planck scale, and the energy required to resolve a region that's small becomes so concentrated that, according to general relativity, it would collapse the region into a black hole before you ever got your answer. The measurement destroys the thing being measured, not because of clumsy equipment, but because gravity itself starts responding to the act of looking. Below that scale, the two best theories we have, the one describing gravity and the one describing the quantum world, stop agreeing on what a measurement even is. We do not actually know that time stops having meaning at that point. What we know is narrower and more honest than that. Our equations, the ones built on a moment always being sliceable into something smaller, stop being trustworthy there. That is a statement about the limits of a map, not a confirmed fact about the territory. Calling it a wall would be claiming more than anyone has actually shown. Calling it fog, a region where our best descriptions blur out and stop resolving anything cleanly, is the most honest word physicists currently have for it. That fog is not mystery for its own sake. It is a specific, calculable point where gravity and the quantum world both insist on having the final word at the same time, and nobody has yet found the sentence that lets them agree. I find it strange, in a way that has nothing to do with the size of the number, that humanity worked out exactly where its own knowledge runs out before it ever built an instrument capable of testing the boundary directly. Most limits get discovered by running into them. This one was calculated from a desk, using constants we already had on hand, decades before anyone could have built anything sharp enough to confirm it firsthand. We knew the shape of our own blind spot before we had any way to look inside it. Nobody has built a clock, and very likely nobody ever will build a clock, that ticks fast enough to look directly at that fog and report back what is actually happening inside it. But a calculated boundary is not the same thing as silence. It is a specific, numerical claim, sitting exactly where the gap between our two deepest theories becomes impossible to paper over any longer. Every serious modern attempt to write a working theory of quantum gravity, whatever shape it eventually takes, uses Planck units as its working currency. The natural scale anything built down there has to be measured against, the same way you would not measure a continent in millimeters. If something in nature really does have a smallest possible tick, a true next moment the way an integer has a next number, this is the only scale where current physics says to go looking for one. A literal smallest tick of time has a real scientific history, and it starts almost a century before anyone had heard of the Planck scale, with a problem inside an equation nobody could make behave. Accelerate an electron and it radiates energy, the same way any accelerating charge does. A basic fact of electromagnetism worked out in the early 1900s by Max Abraham and Hendrik Lorentz. That radiation has to come from somewhere, so it pushes back on the electron's own motion, a kind of friction the particle exerts on itself. Write down the equation for that self-interaction the way Abraham and Lorentz did, and something goes badly wrong with it. The mathematics allows solutions where an electron spontaneously accelerates to enormous speed with absolutely no outside force acting on it at all, gaining energy from nowhere, weeks or months before any actual push arrives to justify it. The deep reason for the trouble is that the equation depends on how fast the acceleration itself is changing, a third derivative of position, a quantity built from slicing time thinner and thinner, one step further than even velocity or acceleration require. Push a mathematical structure to demand an infinitely fine slice 3 layers deep, and it starts producing answers nothing in nature should be able to produce. We call these unphysical solutions runaway solutions, and they have never fully gone away on their own. They sit baked directly into the structure of the equation, not a mistake anyone made writing it down. A handful of physicists across the 20th century, including Pierre Calderola working through the problem seriously in the 1980s, proposed a specific fix: stop allowing time to be sliced infinitely thin for a particle like the electron. Let it advance instead in a smallest possible finite step, a single discrete unit sometimes called a chronon, and rewrite the equation of motion so the particle jumps from one such step to the next, rather than flowing through every smaller interval in between. The step Calderola calculated for the electron specifically came out far larger than the Planck scale, but still smaller than anything any instrument built by human hands has ever resolved directly. Do that, and the runaway solutions disappear on their own, not patched over by hand but actually prevented by the structure of the new equation. The fix was not invented to sound dramatic. It was invented because the standard mathematics, the kind built on a moment always being divisible into something smaller, was producing electrons that gain energy from nothing. That idea never became the field's accepted solution. Modern quantum electrodynamics handles the same runaway problem differently, treating it as an artifact of imagining the electron as a literal point rather than something requiring discrete time at all. The chronon remains a real, carefully worked-out proposal that solved a real mathematical pathology, sitting just outside the mainstream rather than inside it, which is a different and more interesting position than simply being wrong. A second, completely independent road arrived at almost the same destination roughly a century later, built by people who were not trying to fix anything broken in an old equation at all. Working through the 1990s, Abhay, Ashtekar, Carlo Rovelli, and Lee Smolin built a framework attempting to apply quantum mechanics directly to the geometry of space itself, an approach now called loop quantum gravity. Quantum mechanics tends to produce fixed, countable chunks instead of smoothly varying continuously whenever something gets confined, the same underlying reason a guitar string fixed at both ends can only ring out specific notes and nothing in between. The string is free to vibrate however it wants in open air. Pin both ends down, and the confinement itself forces the allowed shapes into a countable list. Confine an electron to the space around a nucleus, and the same forcing produces the fixed, countable energy levels inside every atom, with nothing smoothly in between one level and the next. Apply that same confinement logic to the geometry of space, treating area and volume as quantities a full theory should be able to measure, and the calculation returns something nobody had set out looking for. Area and volume both come out quantized, built from a smallest indivisible unit, the same way the energy levels in an atom are. There is no such thing, in this framework, as a region of space smaller than that minimum unit. Space, examined closely enough, stops being something you can keep cutting in half forever and becomes something closer to a fabric built from a smallest possible stitch. The structure that carries those stitches even has a name borrowed from earlier work. Roger Penrose had sketched something he called a spin network back in the early 1970s, a web of nodes and connecting links meant to build up space itself out of pure combinatorics rather than starting from a smooth background and adding particles to it afterward. Loop quantum gravity picked up that same picture 2 decades later and gave it teeth, turning Penrose's abstract web into the actual carrier of those discrete units of area and volume, each node a tiny quantum of space, each link a quantum of the area separating one piece of space from its neighbor. Space and time are not separate ingredients in general relativity. They are woven into one structure, and a smallest unit on one side of that structure carries real consequences for the other. A theory that hands you a smallest possible patch of space is not naturally compatible with a time variable you can still slice infinitely thin running right alongside it. Picture an old film reel slowed down past the speed it was built to run at. At normal speed, the motion on screen looks completely continuous, a person walking smoothly across a room. Slow the same reel down far enough, and the smoothness breaks apart into separate frames, distinct still images flashing one after another, with real gaps between them that the eye simply could not catch at full speed. 2 separate groups of physicists, working 3 generations apart, solving 2 completely different problems, one chasing a runaway electron and the other trying to quantize geometry itself, both ended up describing reality the way that slowed-down reel looks. Not a flaw in either piece of mathematics. A frame rate showing up uninvited in two unrelated places. Neither proposal has been confirmed by a direct measurement. Both remain serious, carefully reasoned physics sitting outside the settled core of the field, the kind of work taken seriously enough to keep being built on, decades later, by people who are not the ones who first proposed it. What strikes me about placing these two stories side by side is how little they have in common except their conclusion. One came from a frustrated attempt to stop an imaginary electron from accelerating itself out of nowhere. The other came from people deliberately trying to build a new theory of gravity from scratch, decades later, with no electron and no runaway problem anywhere in sight. Nobody copied anybody. Two unrelated paths through two unrelated parts of physics, separated by most of a century, kept landing on the same shape, a universe built from countable steps instead of an infinitely divisible blur. No clock, built by human hands, will ever tick fast enough to catch either kind of step directly, the chronon or the geometric unit underneath it, the way a stopwatch could never catch a single frame inside a film reel running at full speed. If a step that small ever leaves a mark anywhere you could actually find it, the mark would have to travel an enormous distance first, accumulating across a journey long enough to turn an immeasurably small effect into something a large enough instrument might finally catch. That journey already happened, and the instrument that caught it was not a clock at all. It was the entire visible universe, used as a single, patient ruler. In 1998, Giovanni Amelino Camiglia and a small group of collaborators proposed a specific way to use that ruler, aimed squarely at one of the most carefully tested assumptions in all of physics. Special relativity rests on the claim that light moves at exactly the same speed for everyone, regardless of which direction it travels or how much energy it carries, a principle called Lorentz invariance that every experiment for over a century had quietly confirmed without ever managing to rule out a tiny, energy-dependent exception hiding far below detection. If spacetime really does carry a grain at the Planck scale, the way both the chronon and the geometric quantum of space independently suggested it might, light should not be perfectly immune to it. A photon carrying more energy has a shorter wavelength, the same relationship that lets an electron microscope resolve smaller detail than ordinary light ever could, and a shorter wavelength is more sensitive to fine structure than a longer one is, the way a narrow wheel feels every small crack in a road that a wide, soft tire simply rolls straight over. If spacetime has texture at a small enough scale, a high-energy photon should feel slightly more of that texture on its way past than a low-energy photon does, and that difference should translate into an almost unimaginably small difference in how fast each one actually travels. Almost unimaginably small is the entire problem with testing this directly. No laboratory on Earth, no matter how carefully built, has anywhere near enough distance available to let that kind of effect build up into something a detector could register. We need a much longer racetrack than anything available on this planet, and the universe happens to have one already running, for free, every single day. Think of it as a marathon stretched across more than 7 billion years instead of 26 miles. Two photons leave the starting line at the exact same instant, born in the same explosion, one carrying noticeably more energy than the other. If spacetime is perfectly smooth all the way down, both runners cross the entire distance at identical pace and arrive at your detector locked together, exactly as they started. If spacetime has even the faintest texture, the higher energy runner, the one more sensitive to every small bump in the track, falls infinitesimally behind with every single stride, an effect so small per stride that it would never show up over any distance you could fit inside a solar system. Run that same infinitesimal lag for 7 billion years of strides, and even a vanishingly tiny effect has room to turn into a measurable gap at the finish line. A gamma-ray burst is among the most energetic events anything has ever observed. A single explosion, usually the catastrophic collapse of a massive dying star or the violent merger of two neutron stars, that can outshine an entire galaxy of ordinary stars for a few brief seconds. These bursts go off billions of light-years away, far enough that their light has been crossing the universe since long before the Earth itself finished forming, and they release photons across an enormous range of energies all at once, from relatively gentle gamma rays up to some of the most energetic photons astronomers have ever recorded. That spread of energies, leaving the same explosion at the same instant and traveling the same staggering distance afterward, is exactly the setup the 1998 proposal needed. If a small energy-dependent speed difference exists, even one far too tiny to notice over any distance available in a lab, billions of years of travel time gives that difference room to accumulate into something that might finally separate the arrival times enough to measure. In 2009, the Fermi Gamma Ray Space Telescope caught a burst, now catalogued as GRB 090510, that turned out to be close to ideal for the test. It was short, sharp, and intensely bright, producing photons across a huge range of energies in a single tight burst, rather than a long, smeared-out event, which makes it far easier to tell whether photons of different energies truly arrived together or drifted apart along the way. They arrived together. Photons that had been racing each other across more than 7 billion years of cosmic distance, some carrying vastly more energy than others, showed up at the detector within a window of time so tight that it ruled out the simplest version of the effect Amelino Camellia's group had proposed, the kind where the speed difference grows in direct, simple proportion to a photon's energy. Spacetime, at least according to that one race, did not slow the high-energy photons down in the simplest way anyone had predicted it might. A skeptic should ask whether something far more ordinary could fake that result. Dust and gas scattered along 7 billion years of travel slowing some photons more than others, or some quirk of the explosion itself, releasing its highest energy photons a fraction of a second later than the rest, for entirely mundane reasons. Astronomers controlled for exactly that by not trusting any single burst alone, comparing the timing pattern across many separate events at different distances and checking whether the same delay, scaled to the same distance, showed up consistently across all of them, the way a true property of space-time itself would have to. It did not. The tight arrival window held up as a real constraint rather than a coincidence specific to one explosion. We have to be precise about what that result does and does not mean. It is not a discovery that space-time is smooth after all. It rules out one specific, simple shape the graininess might have taken, the easiest version to test, while leaving more complicated versions of the same idea, ones where the effect depends on energy in a subtler way, still standing. Ground-based observatories built specifically to catch extremely high-energy light, working alongside Fermi in the years since, have kept running this same race with newer bursts and other extreme cosmic events, tightening the available room for any energy-dependent speed difference a little further almost every time, without ever once finding a definite signal that such a difference is actually there. That is what a negative result looks like when nobody quietly fudges it into something more exciting, and it deserves real attention rather than a quick dismissal. Nobody gets to announce that space-time is grainy because of this. Nobody gets to announce that it definitely is not, either. What we have is a boundary creeping steadily tighter, race after race, burst after burst, narrowing the space where a real effect could still be hiding without ever quite closing it off completely. I find something almost moving in the fact that we are using catastrophes, the death of stars 7 billion years before anything on Earth had a name for catastrophe, as a measuring tool for something this intimate, this small, sitting inside the structure of a single moment. The explosion does not know it is being used this way. It is simply the brightest, most extreme thing physics could throw at the problem, repurposed by people patient enough to wait billions of years for an answer that, so far, has only ever come back as not yet. If the grandest, most violent events the universe can produce are being recruited as instruments for something this small, it is worth asking whether anything closer to home, something built from ordinary cells rather than a dying star, has ever brushed up against a limit of its own that works the same way. Your own eyes are doing it right now, in whatever light is left in the room around you, resolving the world at a fixed rate and calling the result continuous. Flash a light on and off fast enough, and at some point you stop seeing individual flashes and start seeing one steady glow instead. That switchover point has a name, the flicker fusion threshold, and for most people under ordinary indoor lighting, it sits somewhere around 50 to 60 separate flashes every second. Slower than that, and your eyes catch every individual pulse, a visible strobe. Faster than that, and the pulses blur together into something that looks, feels, and behaves exactly like continuous light, even though nothing about the light itself changed. Only your ability to keep up with it did. That threshold is not fixed the way a law of physics is fixed. Push the brightness of the flashing light up, and the threshold rises with it. A relationship called the Ferry-Porter law, after the two researchers, working a decade apart in the 1890s and again in 1902, who first measured how cleanly flicker fusion frequency tracks the logarithm of light intensity. A dim flicker fuses into smoothness at a fairly low rate. A bright one needs to flash faster before your eyes stop catching the gaps. Your own retina is not running one fixed frame rate at all. It is running a frame rate that depends on how much light is actually available to work with. It also depends on where the light lands. Your peripheral vision, built mostly from light-sensitive cells called rods, fuses flicker at a noticeably higher rate than the cone-dominated center of your gaze does, which means something flickering gently at the edge of your visual field can register as a steady light, while that exact same flicker held dead center, where you would swear your vision is sharpest, can still read as a visible pulse. The part of your eye you trust the most for detail is, in this one specific way, the slower part. It is the reason an old fluorescent tube or a cheap screen can look rock steady the moment you stare straight at it, yet seem to shudder faintly the instant it drifts toward the corner of your eye. Nothing about the light changed when that happened. Only which part of your retina was doing the sampling did. We have known something was happening here since well before anyone understood the biology behind it. In the 1820s, a Belgian physicist named Joseph Plateau became fascinated with how an afterimage lingers once a bright light disappears, and pushed that fascination further than most people ever would. Staring directly at the sun for nearly half a minute to study the afterimage, it burned into his vision. He spent the following decades going gradually, permanently blind, a price almost certainly connected to that early experiment among others, even as the persistence of vision he had set out to understand became the founding principle behind animated toys, then film, then everything that followed it. What none of that 19th century work anticipated is how differently the same threshold sits in other eyes, and the differences are not random. A trained pigeon can be taught to respond to flicker rates that fuse into smoothness for it only above roughly 100 flashes per second, nearly double what most human eyes require, useful for a creature that has to track the exact wing beat and flight path of a rival or a predator against open sky. Dogs sit a bit above us as well, which is part of why an old television, perfectly steady and watchable to the people in the room, could look like it was visibly strobing to the dog lying in front of it. Houseflies push the number further still, with eyes built to resolve flicker at rates climbing toward 250 flashes per second or more, an adaptation that makes sense the moment you remember what a fly actually has to do with its vision, dodging a hand moving toward it in a fraction of the time a human nervous system needs just to notice the hand has moved at all. A faster frame rate is not a luxury for an animal whose entire survival depends on reacting to things that move quickly. It is the minimum equipment the job requires. A hummingbird's wing beats somewhere between 50 and 80 times every second, depending on the species. To you, watching with a visual system tuned to a lower threshold, that wing dissolves into a single soft blur, a smear of motion with no individual strokes visible anywhere inside it. To an insect with a flicker fusion rate well above that wingbeat frequency, there is no blur there at all. There is only a wing, moving through a series of distinct, separately visible positions, one after another, each one as sharp and countable as a single frame. Nothing about the wing changes between those two viewings. Only the resolution of the eye doing the watching does. The same motion is, at once, a perfect blur and a series of distinct, separated events, depending entirely on what kind of instrument happens to be looking at it. A careful listener might object that biology proves nothing about physics, that a retina running out of integration time has nothing real to say about whether space-time itself has a texture. That objection is fair on its own terms, and the claim was never that it does. What the eye does offer, cleanly and without any speculation attached to it, is a working example of the exact failure mode this whole question depends on. A system can sample reality at a finite rate, blend everything faster than that rate into one smooth impression, and never once notice that anything was missing, because the system doing the noticing is the same system doing the blending. That is not a metaphor borrowed from biology to decorate a physics question. It is the same structural problem, observed and measured directly, in an organ sitting inside your own skull. The mechanism underneath your own threshold is not the same one that gives a neuron its hard refractory period. It runs one level up from any single cell, in how long your visual system takes to integrate incoming light into a single usable signal before passing it forward, a brief window of averaging that smooths anything happening faster than itself into one blended impression. Speed up whatever is flickering past that integration window, and the system simply runs out of time to register the gaps before the next flash arrives to be averaged in with it. You are not a passive witness to a smooth world. You are an active participant in manufacturing the smoothness, sampling reality at a rate your own biology sets, then quietly discarding the question of what happened between samples because nothing in your visual system was ever built to ask it. If something this intimate, the basic feeling that the room around you holds together as one continuous scene rather than a sequence of separate frames, turns out to be generated by the limits of the instrument doing the looking rather than supplied by the world itself, the open question worth carrying forward is whether the sense that time itself flows could be built the exact same way, manufactured from the inside by whatever is doing the experiencing rather than handed down from outside by the universe. You never know everything about any system you are looking at, and that single, ordinary admission turns out to manufacture a flow of time all on its own, with nothing else required. Take the air in the room around you right now. You can know its temperature. You can know its pressure. You will never know the exact position and exact speed of every single molecule bouncing around inside it, not because the information is hidden somewhere, but because no measurement could ever extract that much detail from a system that large. We handle this gap by describing the air statistically instead. A thermal state, a description built entirely out of what you do not know rather than what you do, treating billions of unmeasured possibilities as equally likely and working with the average instead of the impossible full picture. In 1967, a mathematician named Minoru Tomita discovered something strange about exactly this kind of statistical description in a piece of pure mathematics that had nothing to do with physics, time, or the real world at all. Tomita was studying structures called von Neumann algebras, abstract mathematical objects used to describe collections of measurements you could perform on a system. He found that any time you hand one of these structures a thermal, statistical state, the kind built from incomplete knowledge, the mathematics automatically generates something extra alongside it, a flow, an ordering, a built-in notion of before and after, sitting inside the state itself, that nobody had to add by hand. Hand the same mathematics complete information instead, a state where nothing is left unknown, and the automatic flow collapses to nothing, sitting perfectly still with no ordering generated at all. The flow is not a universal feature every state produces equally. It only switches on for states built out of missing information, which makes incomplete knowledge, not some extra ingredient added afterward, the actual source of the ordering. Masamichi Takesaki refined and extended the result over the following years, and the combined work became known as Tomita Takesaki theory, filed away for 2.5 decades as an elegant piece of mathematics with no apparent connection to physics whatsoever. In 1994, Elaine Kahns and Carlo Rovelli looked at that filed-away result and asked a question almost nobody else had thought to ask. What if that automatic flow is not just a mathematical curiosity? What if it is time itself? Their proposal, now called the thermal time hypothesis, is more radical than it first sounds. In a theory built to describe the entire universe at once, the kind general relativity and quantum mechanics are still struggling to merge into a single framework. There is no external clock sitting outside the system to hand it a flow from above. Kahns and Rovelli suggested that none is needed. Describe any physical system using a thermal state, the same kind of incomplete statistical description physicists already use constantly out of practical necessity, and a flow falls directly out of the Tomita Takesaki mathematics, automatically, without anyone supplying it from outside. Time, on this proposal, is not a stage the universe happens to be performing on. It is something a system generates for itself the moment it is described statistically rather than completely. That consequence cuts hard against the picture most explanations of time hand you by default. The flow this mathematics produces is not attached to the universe as a single whole. It is attached to whichever thermal state you happen to be using to describe a system. Change the state. Change what you choose to treat as known and unknown about the same underlying reality, and the flow generated by the mathematics can change with it. Two different statistical descriptions of the very same physical situation are not guaranteed to generate the same notion of before and after. Go back to that same room full of air. Describe it the way you actually can, knowing only its temperature and pressure, and the Tomita Takesaki mathematics hands that description of flow, a real, mathematically generated ordering running through it. Now imagine a different observer, one with some impossible instrument capable of tracking the exact position and exact velocity of every molecule at once, leaving nothing statistical about the description at all. That second observer is looking at the identical air, in the identical room, at the identical moment, and the same mathematics hands their description no flow whatsoever, because nothing about it was ever incomplete to begin with. Same room, same air, same instant. Two different amounts of missing information, and two completely different answers to whether time is flowing through it at all. We should be precise about where this idea actually stands. It is not a settled result the way the flicker fusion threshold of a human retina is settled. It is an active, contested proposal, built on real, rigorously proven mathematics applied to physics in a way specialists still argue about, particularly over how this thermal flow relates to the ordinary, ticking proper time a physical clock would actually measure, and over what happens to the proposal once a system sits away from a clean, stable equilibrium. Nobody has built an experiment that confirms or rules it out yet. What it offers us is not an answer so much as a working demonstration that flow does not have to be handed down from outside a system at all. It can, mathematically, be generated from inside one, by nothing more exotic than the simple fact that nobody ever knows everything. The proposal does connect to one independently discovered piece of real physics, which is part of why it gets taken seriously rather than dismissed outright. In the 1970s, the physicist Bill Unruh showed that an observer accelerating fast enough through completely empty space would perceive that emptiness as warm, filled with a faint bath of thermal radiation that a stationary observer right beside them would not detect at all, an effect derived independently with no reference to Tomita or Takesaki or any thermal time hypothesis whatsoever. Canes and Rovelli showed that their thermal flow, applied to an accelerating observer, predicts a temperature for exactly that effect, matching what Unruh had already derived through a completely separate calculation years earlier. Two pieces of mathematics, built for entirely different reasons by people working decades apart, landed on the same number. There is something quietly destabilizing about that. Every account of time covered up to this point, the granular structure of the smallest possible interval, the speed limit on how fast anything is allowed to change, the discrete ticking inside a single cell, has still assumed there is one underlying flow, that all of those things are happening within. The thermal time hypothesis does not assume that. It suggests the flow itself might be a local production, generated separately by whatever system happens to be doing the describing, built fresh each time out of nothing more than incomplete knowledge. If a flow of time can be generated from the inside, manufactured by a system out of its own statistical state rather than handed to it from somewhere outside, the next question follows almost on its own. What kind of flow does that mathematics generate for a system built the way you are built right now, lying still, breathing, carrying a very particular, very specific kind of incomplete knowledge about itself? Two separate locks turn out to be sitting on the exact same door, and neither one was ever in your hands to begin with. The first lock is energy. How fast you are allowed to change from one state into a measurably different one is capped by how much energy you carry above your own lowest possible floor. The same bound that governs an electron, a trapped ion, a crystal cooled within reach of absolute zero. Nobody handed you that cap from outside. It is set by what you happen to be made of and how much of it is moving. The second lock is information, or rather the lack of it. The flow you experience, the sense that there is a before and an after it all, is not necessarily something poured into you from some master clock running the universe. It may be something generated from the inside, manufactured automatically by the simple fact that no description of you, including your own, was ever complete. Two locks, turning independently, both keyed to the exact same object. Not the universe, not some external schedule. You, specifically, as a physical system. Put them together and something sharper comes into focus than either one offers alone. The cap on how fast you can change is set by your energy. The flow you change within is set by your incompleteness. Neither number was assigned to you by anything outside yourself. Both were generated, separately, by what you already are. Combining these two results might sound like placing two unrelated pieces of mathematics next to each other for effect. They are not unrelated. Both concern the exact same object, the quantum state used to describe a physical system, looked at from two different angles. The energy bound reads off how much usable energy that state carries above its floor. The thermal flow reads off how much information that state is missing. They are two separate measurements taken from the same description, not two separate stories stitched together for atmosphere. Think of an instrument that builds its own rhythm rather than receiving one. A plucked string does not wait for a conductor standing somewhere outside the room to tell it how fast to vibrate. Its tension, its length, its mass per unit length decide that on their own, baked directly into the physical object before anyone ever touches it. Pluck it, and the rhythm that comes out was never handed down. It was already sitting inside the string, waiting on the specific physical facts of what that string happened to be built from. You are a far stranger instrument than a single string, because you are not one system tuned to one rhythm. You are an almost unimaginably large collection of smaller systems, each one carrying its own energy, each one describable only statistically, layered inside each other. A single neuron has its own cap on how fast it can fire again, set by its own energy and its own refractory machinery. A heart cell has its own. Every one of the roughly 37 trillion cells making up the body you are lying in right now is, in this narrow technical sense, its own small instrument, generating its own small piece of flow out of its own small slice of incompleteness. What holds all of those separate instruments together into the single, unified sense of, now that you are experiencing this sentence inside, is not yet understood, and it is worth being honest about the size of that gap. Nobody has calculated what any of these numbers actually equal for a system as layered as a human body. The mathematics exists at the level of single particles, single crystals, single idealized systems simple enough to solve cleanly. It has never been run on something built from trillions of interacting, overlapping, mutually adjusting smaller systems, all generating their own local flow at once, somehow producing the seamless, singular experience you are having right now, instead of trillions of separate, disconnected ones. That gap is not a reason to dismiss the question. It is the actual shape of where the open problem sits. We are not waiting on physics to tell us whether time is real. We are waiting on physics to catch up to a calculation about a system this complicated, one that nobody currently knows how to perform. Notice what neither lock actually depends on. Neither one asks what you believe, what you remember, or how aware you happen to feel at any given moment. They are facts about the arrangement of energy and the incompleteness of any description of that arrangement, the same kind of fact that applies to a crystal or a single trapped atom, not a verdict on your character or your state of mind. That is worth being precise about, because it is easy to hear a sentence like a limit on how fast you can become someone different and slide straight into something far more dramatic than the physics actually supports. The rate at which you are allowed to become someone slightly different than you were a moment ago answers to your own energy, not to anything borrowed from outside, regardless of whether anyone ever finishes that calculation. The flow you are experiencing that change within answers to your own incompleteness, not to a master schedule running somewhere else. Both numbers, whatever they actually equal, belong to you the way the rhythm in a plucked string belongs to the string and not to the hand that plucked it. None of this sits at a comfortable distance from you the way a gamma ray burst 7 billion years away does. Every thought finishing inside you right now, every shift from the version of you that started this sentence to the version of you finishing it, is itself an instance of the exact state change. Both locks are quietly governing while it happens. The open question is not sitting out in a laboratory somewhere, waiting for someone else to resolve it. It is running, continuously, inside the same system that is currently reading these words. So the question worth carrying forward is not whether a limit exists. The energy bound and the thermal flow both already say one does. The question is, what that limit actually comes out to for a system built the way you specifically are built, and whether it is wider than you would ever need in an ordinary life, or closer than anyone has been comfortable calculating. For a warm, ordinary body like the one you are lying in, the limit on how fast you can change sits so far out of reach that nobody has ever needed to think about it. For one category of machine humans have actually built, it does not sit far out of reach at all. A quantum computer performs its basic operations, called gates, by nudging a qubit from one quantum state into another. The same kind of state, change the energy-based speed limit governs directly. Superconducting qubits, the kind IBM and Google have both built entire processors out of, typically execute a single gate in tens of nanoseconds, billionths of a second, using an energy difference between quantum states that engineers chose specifically because it sits in a range modern electronics can actually control. Run the Margolis-Levitin mathematics on that specific energy difference, and the absolute fastest a gate could possibly execute, no matter how perfect the engineering became, comes out within a small handful of orders of magnitude of the gate speeds already achieved in real labs. Your own body sits separated from its theoretical limit by a gap too vast to write out comfortably. A modern qubit sits separated from its limit by a gap you could fit on one hand. Pushing a qubit's energy higher would push its theoretical speed limit higher too, and engineers know this perfectly well. They do not simply crank the energy up, because a second clock is running at the same time, working against the first one. A qubit holds its quantum information only for a limited stretch before the surrounding environment, stray heat, stray electromagnetic noise, nearby atoms vibrating in ways nobody can fully isolate, leaks in and scrambles it, a process called decoherence. Superconducting qubits trade speed for that fragility, executing gates in nanoseconds but losing their information after only a few hundred microseconds. Qubits built from individually trapped ions take the opposite trade, holding their information cleanly for seconds or longer while accepting gates that run thousands of times slower. Neither choice gets a platform closer to the absolute energy bound for free. Every real qubit is fighting the same two limits at once. One set by how much energy it is allowed to carry, the other set by how long it is allowed to keep its answer, before the universe quietly erases it. That closeness is not an accident of marketing. It is the entire reason the bound was discovered in the first place. When Norman Margolis and Lev Levitin published their result in 1998, they were not investigating an abstract curiosity about quantum states in general. They were explicitly asking how fast a computer, any computer, built from any physical material whatsoever, could possibly run, and derived their bound as the answer. The energy-based speed limit on change began its life as a hard ceiling on computation itself, decades before anyone had built hardware precise enough to bump up against it. Seth Lloyd pushed that same question to its absolute conclusion in the year 2000, in a calculation that is still cited constantly inside quantum computing research today. Take a kilogram of matter, about the mass of a small laptop, and compress every joule of energy locked inside it. All of it, using Einstein's equivalence between mass and energy, rather than just the small fraction any ordinary battery or processor actually taps into. Feed that full amount of energy into the Margolis-Levitin bound, and the result is a theoretical ceiling of roughly 10 to the 50th operations every single second, a number so far beyond anything built that comparing it to a real machine barely helps. The fastest supercomputers running today, machines built from rooms full of custom processors and pulling enough electricity to power a small town, complete somewhere around 10 to the 18th operations per second. The gap between what we have actually built and what 1 kilogram of matter is permitted to do under the absolute laws of physics is itself a number with more than 30 zeros in it. That ceiling is not a blueprint anyone could follow. A kilogram of matter converting all of its mass into pure computational energy at once would not behave like a laptop. It would behave like a small black hole, compressed past the point where ordinary matter survives as matter at all. Lloyd's number is not an engineering target. It is a boundary condition, a statement about what the laws of physics will permit before they stop permitting anything resembling a computer to exist at all, calculated as a true ceiling rather than aimed at as a target. Lloyd's paper did not stop at speed. A computer also needs somewhere to keep its answers, and that question has its own absolute ceiling, discovered decades earlier and for entirely unrelated reasons. In 1973, the physicist Jacob Bekenstein working on the thermodynamics of black holes rather than anything to do with computers, proved that any bounded region of space, holding a fixed amount of energy, can contain only a finite, calculable amount of information before adding more, would require so much additional energy that the region collapses into a black hole on its own. Apply that same bound to Lloyd's kilogram, squeezed into a volume the size of a liter, and the absolute ceiling on how much it could ever remember comes out to roughly 10 to the 31st bits, a number that, like the speed limit sitting next to it, was never designed with computers in mind and turned out to govern them anyway. Real quantum computers are nowhere near that ultimate ceiling, and they are not trying to be. What makes them worth dwelling on is a narrower, more concrete fact. Among every system humans have ever deliberately built, ultra-cold, carefully isolated qubits sit closer to their own personal version of the absolute speed limit than anything else humanity has constructed, closer by a staggering margin than your own warm, energetic, thoroughly imperfect body sits to its own. Put that gap in concrete terms and it stops being an abstraction. A single neuron in your brain fires at most a few hundred times a second, a rate set by the refractory machinery covered earlier rather than by any shortage of energy. Nobody has carried out the full calculation for something as biologically tangled as a real neuron, and that complexity deserves to be stated plainly rather than glossed over with an invented number. What is not in question is the direction of the gap. The energy already sitting inside a single firing neuron is nowhere close to the limiting factor on its speed, the way it is for a qubit pushed right up against engineering's current edge. A neuron is not straining against its own ceiling. A modern qubit is built specifically to strain against exactly that. That gap between a qubit and a body is not really about technology at all. It is about how much spare energy above its own floor each system happens to carry, relative to how fast it is actually being asked to change. A qubit is stripped down, cooled, isolated, holding almost no energy beyond exactly what its designers gave it on purpose, every joule accounted for, and aimed directly at the one state change it needs to make. Your body is none of those things. It carries enormous amounts of energy doing thousands of unrelated jobs at once, almost none of it aimed at any single specific state. Change the way a qubit's energy is, which is precisely why you never come close to bumping into your own version of this limit during an ordinary life. If the closest thing humanity has ever built to the universe's actual speed limit on change is a sliver of matter cooled and isolated on purpose for exactly that reason, the open question that follows is what that same absolute mathematics actually predicts, without flattering anyone, for the warm, busy, completely uncooled system currently reading these words. None of this has ever been about distance from a limit. It has been about whether a limit was ever optional in the first place, and it was not. Every thread followed so far has been circling toward this same point from a different direction, a continuum that may not be as smooth as the mathematics assumed. A hard floor under how fast any system is allowed to change. Cells and hearts and synthetic crystals, all keeping their own discrete time without asking permission from anything outside them. A flow that mathematics can generate from nothing but incomplete information, with no master clock required to supply it. None of those threads were ever just about electrons, or crystals, or the universe at large. Every one of them was quietly also a description of the exact thing reading these words right now. You have spent your entire life assuming that changing your mind, noticing something new, shifting from not understanding a sentence to understanding it, was a kind of freedom, the one part of you that operated outside the accounting every other physical process has to obey. It does not. Every single one of those changes is a physical transaction, paid for in real energy you happen to have on hand, governed by the exact same mathematics that caps a qubit and caps an electron. You were never exempt from the bookkeeping. You were always inside it. Every single time you became even slightly different than you were a moment before. That energy is not an abstraction borrowed for the sake of argument. It has a name, a specific molecule called adenosine triphosphate, manufactured continuously inside structures called mitochondria, spent in countable packets every time a muscle fiber contracts, every time a thought requires a neuron to fire, every time anything inside you becomes a version of itself. It was not a moment earlier. Your brain makes up roughly 2% of your body weight and burns through close to a fifth of your entire resting energy budget, a wildly disproportionate share spent specifically on the business of becoming a slightly different configuration from one instant to the next. Thinking has a receipt. It has simply never been a receipt you are handed to read. The reason that bookkeeping has never once felt like a constraint is not that you are free of it. It is that you have never come close to spending what it would take to feel it. A qubit, stripped down to almost nothing but the energy needed for one specific job, runs hard against its own ceiling on purpose. You carry enormous reserves of energy doing thousands of unrelated things at once, almost none of it aimed at any single change the way a qubit's energy is, which is exactly why the cap has stayed invisible to you for as long as you have been alive. Invisible is not the same as absent. It only ever meant unspent. The flow you are changing within was never supplied to you either. It was never a current running through the universe that happened to pick you up and carry you along with everyone and everything else. The mathematics says a flow gets generated, locally, by the specific incompleteness of whatever system is being described, the same way a plucked string generates its own pitch out of its own tension, rather than borrowing one from outside. Look at how incomplete that description of you actually is. At this exact moment, your immune system is reading signals from your gut, your heart rate is shifting in patterns tied to your breathing, hormone levels are rising and falling in rhythms set hours ago, and almost none of that activity will ever reach the part of you having this thought. The brain does not track the literal state of every cell it governs. It works from a compressed, statistical summary, the same kind of incomplete description Tomita's mathematics requires before it will generate a flow at all. Your felt sense of being one continuous person moving through one continuous now may be exactly what that compression produces. Not a window onto some complete, unified truth about yourself, but the specific output of a system that was never given and was never built to want the full picture. That compression runs deeper than gut signals and hormones. Even the version of yourself you are consciously aware of right now, the sense of being a single, continuous someone reading this sentence, is itself a statistical summary your brain builds about its own state, not a direct readout of it. You are not just incompletely informed about your body. You are incompletely informed about your own mind. Using a compressed model of yourself to think about a compressed model of yourself, one layer of missing information generating a flow inside another layer of missing information, all the way down as far as anyone has ever managed to look. The rate at which you are allowed to become someone new answers to energy you happen to carry, paid out in actual molecules, inside actual cells, on an actual schedule. The flow you become someone new within answers to information you happen to lack, compressed and recompressed by a brain that was never given and never asked for, your complete state. Neither one was ever handed to you from outside. Both were always, from the very first moment you existed, internally generated, accounted for, paid for, the way they are for an electron or a crystal or a qubit cooled near absolute zero. There was no separate version of you standing apart from that accounting, watching it happen from somewhere safe. The accounting was you. This is not a warning that something is about to run out. Nothing in what has been laid out so far suggests you are anywhere near a ceiling that should worry you. What it suggests is narrower and in its own way harder to settle into. The part of you that has always felt like it stood outside physics, the part doing the noticing, the changing, the understanding, was never standing outside anything. It was always exactly as physical, exactly as accounted for, exactly as governed by energy and incompleteness, as the coldest, most carefully isolated qubit in any laboratory on Earth. That does not make the thought you are having right now less real. It makes it exactly as real as a physical transaction actually is, with nothing borrowed, nothing exempted, and nothing standing outside the ledger to watch it happen for free. The opening question was whether a moment could always be sliced into something smaller, forever, with no bottom anywhere underneath it. Whatever the answer to that question eventually turns out to be at the scale of spacetime itself, it is no longer the only place the question matters. It is sitting, right now, inside a system spending real molecules to become someone slightly different than it was a sentence ago, using a flow it manufactured out of its own incomplete knowledge of itself, with no outside authority required to grant either one. Anyone who has followed this reasoning carefully has every right to ask how confident a person can actually be in a conclusion this large, built from results this specialized, this contested, this far from finished. That question deserves a real answer, not a reassurance. A careful physicist would not let any of the last several claims stand without pushing back hard, and the pushback deserves to be heard in full rather than waved away. The sharpest objection targets the idea of a literal lattice underneath spacetime, a fixed grid with a smallest possible spacing, the way a chessboard has a smallest possible square. Special relativity makes a demand that a naive grid like that cannot satisfy. Two observers moving at different speeds relative to each other measure lengths differently, a real, repeatedly confirmed effect called length contraction. If spacetime really were a fixed grid with one true spacing, observers moving at different speeds would measure that same grid spacing differently, which means at least one of them would be looking at a grid that is no longer evenly spaced from their point of view. A discreteness built the simplest, most literal way breaks one of the most thoroughly tested principles physics has. The same principle the gamma-ray burst race tested directly and found no violation of. That is not a minor technical wrinkle. It is the reason most serious theorists rejected the simplest version of discreteness decades ago, long before anyone needed a gamma-ray burst to rule it out experimentally. That objection did not end the search. It redirected it. Starting in the 1980s, the physicist Raphael Sorkin and a small number of collaborators asked whether discreteness could be built without a regular grid at all. Their approach, called causal set theory, throws out the idea of fixed spacing entirely and replaces it with something closer to a vast, irregular scatter of individual points connected only by which ones could have influenced which others, a structure built from cause and effect rather than from distance. A random scatter like that has no preferred spacing for different observers to disagree about, because it has no spacing in the ordinary sense to begin with, only relationships. The randomness is not a shortcut taken to dodge the problem. It is mathematically required by it. Sorkin and his collaborators showed that scattering points using true randomness, the same kind used to generate noise that has no pattern an observer could lock onto, is what keeps the resulting structure compatible with the demand that nobody's measurement of speed or length gets singled out as the correct one. A regular grid hands every observer something to disagree about. A sufficiently random scatter hands nobody anything regular enough to disagree over in the first place. It is a deeply strange way to try to rebuild a smooth-seeming universe from discrete pieces, and decades of work have gone into checking whether anything that irregular could actually reproduce the smooth physics we already know works. The jury inside the field is still out. A second, equally serious position inside physics says all of this discreteness talk may be solving a problem that does not exist. Continuum physics. The kind built on a moment always being divisible into something smaller, has worked without a single confirmed failure for 3.5 centuries. Quantum field theory and general relativity, each treating spacetime as smooth, both match observation to a precision that borders on absurd. Researchers who study quantum gravity carefully, including physicists like Sabine Hossenfelder, have argued in public and in print that the case for a minimum length or a fundamental graininess is, at this point, a mathematical preference rather than a result anyone has actually been forced into by data. Elegant does not mean true. A theory can be beautiful, internally consistent, and motivated by real, deep reasoning, and still turn out to describe a universe that is not the one we live in. The absence of a detected violation in the gamma-ray burst tests covered earlier is not neutral information sitting quietly on the sidelines. It actively narrowed the field. The simplest, most naive lattice models, the ones easiest to rule out, are largely ruled out already. What survives are the harder, stranger proposals, causal sets among them, built specifically to dodge the Lorentz invariance problem from the start, alongside the live possibility that nothing is grainy at all and the smoothness was real the entire time. Even researchers who do think some form of discreteness is likely cannot currently agree on which version is correct. String theory points toward a minimum length built into the size of its fundamental strings. Loop quantum gravity points toward discrete units of area and volume arranged in a spin network. Causal set theory points toward a scatter of points with no geometry at all until relationships are added. These are not three descriptions of the same idea wearing different clothes. They make different mathematical claims, and at least some of them must be wrong if any one of them is right. Resolving any of it will not come from a single decisive experiment arriving all at once. It will come the way the gamma-ray burst tests already came, in increments, each new observatory and each new burst tightening the available room a little further, each new generation of gravitational wave detectors checking whether ripples in space-time itself carry any trace of the texture these theories predict, slowly squeezing the space where a wrong idea could still be hiding rather than producing one announcement that ends the argument outright. That is a slower, less satisfying kind of progress than a single proof. It is also the only kind serious physics has ever actually delivered. None of that uncertainty is a weakness to be embarrassed about. It is what an honest, unfinished piece of physics actually looks like from the inside, before history decides which thread turns out to matter and which gets quietly set aside. The discomfort the previous discussion landed on does not get to borrow false certainty from physics in order to feel more solid than it is. It has to stand or fall on results that are still being argued about by the people closest to them. A claim that survives only because nobody has bothered to attack it properly is not a strong claim. It is an untested one wearing the costume of a strong one. Everything in this disagreement, the lattice problem, the causal sets built specifically to dodge it, the researchers who think the entire question may be solving nothing real, deserve to be said plainly rather than smoothed over to protect a tidier story. What nobody on any side of that disagreement disputes is one specific piece of evidence that never depended on theory at all, sitting in a laboratory rather than in a debate, cold enough and isolated enough to already be doing, on a workbench, exactly what the disagreement above is still arguing whether the rest of the universe does. That workbench has not stayed still since the first crystals were built. The question stopped being whether matter could keep its own discrete time at all, and became how far that discreteness could actually be pushed. The earliest demonstrations used a chain of a few trapped ions, or a small patch of defects inside a single diamond, systems chosen specifically because they were small and clean enough to control completely, a result that only shows up in one exotic, hand-built setup always invites a fair question. Is this a real phase of matter, or a quirk belonging to that one particular piece of hardware? In 2021, a team working with Google answered that question by building a time crystal somewhere nobody expected to find one, inside a programmable quantum processor, the same general kind of chip built for quantum computation rather than for studying exotic phases of matter on purpose. That processor let researchers drive dozens of qubits at once, with a precision no trapped ion chain or diamond sample from the earlier generation could match, and the same stubborn refusal to follow the driving rhythm showed up again, locked in, robust against the kind of small imperfections that would have washed out an ordinary resonance. Finding the same phenomenon on completely different hardware, built for an entirely different purpose, is the strongest kind of confirmation a new phase of matter can get. It stopped being a curiosity that happened to occur inside one lab's particular apparatus and became something closer to a property of quantum matter itself, reproducible anywhere the right conditions are assembled. Telling a real-time crystal apart from an ordinary system that merely looks periodic for a little while is its own careful piece of work. Almost anything pushed hard enough will ring for a few cycles before settling down, the way a struck bell rings and fades. What distinguishes a real-time crystal is that the ringing does not fade. Researchers test this specifically by deliberately roughening the system, adding disorder to individual qubits or detuning the drive slightly off its clean rhythm, and checking whether the locked, half-rate response survives that roughening anyway. A struck bell goes quiet sooner under that kind of interference. A real-time crystal keeps its rhythm regardless, which is the actual signature researchers look for before calling anything by that name. A skeptic could reasonably ask whether a result built on a quantum computer is really evidence about nature, or just a clever piece of engineering doing exactly what its designers told it to do. The distinction matters here for a specific reason. The processor was not built to chase a time crystal on purpose. It was built for general quantum computation, and researchers simply programmed it into the right configuration afterward and watched the same locking behavior emerge unprompted. We were not engineering the effect into existence. We were finding out that the hardware already had it in it, the same way the trapped ions and the diamond defects did, without anyone designing for that outcome from the start. The deeper frontier now sits past, the kind of time crystal already described, the kind built from a chain of trapped ions or a patch of diamond defects. Every version built so far has been a Floquet time crystal, meaning it only exists while something outside keeps tapping it at a steady rhythm, refusing to match that rhythm, but still depending on it to exist at all. The original, more radical version Frank Wilczek first imagined, a crystal that ticks entirely on its own with nothing driving it, was proven impossible years ago, but only for a system sitting in true equilibrium, sealed off and balanced, with nothing flowing in or out. Researchers have started building systems that are not sealed off in that way, kept slightly open, with energy and particles trickling in and dissipating back out continuously rather than sitting in a closed equilibrium. That openness changes the rules the original no-go proof depended on, because the proof only ever covered systems with nowhere for energy to come from or go to. Several groups working with atoms held inside optical cavities, driven gently and continuously rather than tapped in discrete pulses, have now reported time crystalline behavior in exactly this kind of leaky, open system, ticking on its own internal rhythm while something flows steadily through it, edging closer to Wilczek's original picture than the Floquet crystals built so far ever could. Nobody is claiming the equilibrium no-go proof was wrong. They found the door it had left open the entire time and walked through it. None of this stays confined to a curiosity cabinet either. A system whose internal clock locks in and resists small disturbances is, by that exact same property, an unusually stable timekeeper. Researchers studying quantum sensing have started asking whether the same stubbornness that makes a time crystal interesting as physics could make it useful as a tool, a clock or a sensor whose rhythm holds steady against the kind of small noise that degrades an ordinary oscillator. If that work succeeds, the device sitting in your pocket a decade from now, correcting your phone's position by satellite, could, in principle, be running on a sliver of matter keeping discrete time on its own, just engineered on purpose instead of stumbled into. Nobody has built a practical device yet. The direction of the research has shifted, in less than a decade, from proving something this strange could exist at all to asking what it might be used for. Watching this move from one exotic chain of ions to a programmable chip to an open, continuously driven system in the space of less than 10 years, the pace itself is worth noticing. A result that sounded almost too strange to be real turned into a research program with momentum, collaborators, and a roadmap, fast. That speed is usually a sign that a phenomenon is not a fluke. Flukes do not survive being chased this hard by this many independent groups for this long. A few grams of matter, cold and carefully isolated, can already do this. The harder question left standing is what happened at the one moment in the history of the universe when matter was neither cold nor carefully isolated at all, compressed instead to a density and a temperature that makes a dilution refrigerator look like the gentlest environment physics has ever built. We can trace the history of this universe backward with real confidence to roughly a trillionth of a second after it began. And then the confidence runs out faster than most people ever get told, falling away into a gap nobody likes to admit is there. That trillionth of a second mark is not arbitrary. It corresponds to energies the Large Hadron Collider actually reaches when it smashes protons together, which means the physics governing the universe at that age is not speculation. It is physics we have recreated and measured directly, here, on Earth, inside a ring of magnets under the border of France and Switzerland. Push back further, toward what cosmologists call inflation, a period of expansion so violent it stretched the universe by a factor large enough to turn a single point smaller than a proton into something the size of a grapefruit in a fraction beyond a trillionth of a second, and the confidence thins out considerably. Inflation is well motivated. The patterns it predicts show up in the faint afterglow of the early universe astronomers can still observe today, but it is supported by fit to evidence, not by recreating the conditions directly the way a collider does. Inflation is usually dated to a window starting somewhere around 10 to the negative 36th seconds and ending somewhere around 10 to the negative 32nd seconds, depending on which specific model is doing the dating. Even the later edge of that window still sits an almost incomprehensible distance from the Planck time covered earlier, a gap spanning roughly 11 more orders of magnitude of pure, undocumented territory. That gap is not a thin seam between two well-understood eras. It is the single largest stretch of cosmic history where physics currently has nothing to stand on, wedged directly between the best supported theory we have and the smallest interval the mathematics can even describe. Closing that gap with an actual experiment is not a matter of better funding or a cleverer team. Reaching collision energies anywhere near the Planck scale directly would require a particle accelerator with a ring large enough to wrap around the disk of the Milky Way several times over, built from magnets stronger than any material currently known how to manufacture, cooled colder than anything currently built to stay cold. That is not an engineering challenge waiting for a sufficiently determined billionaire. It is a request for an instrument larger than the galaxy containing the civilization that would need to build it. So when the question turns to what actually happened in that gap, including the very beginning sitting on the far side of it, the honest answer starts by rejecting a phrase almost everyone has heard. General relativity, run backward to the literal beginning, predicts a singularity, a single point where density and the curvature of spacetime both rocket toward infinity. Almost no cosmologist treats that prediction as a description of physical reality. It is treated as a signal that general relativity itself has stopped being trustworthy, the exact same kind of breakdown covered earlier when energy concentrated into too small a space collapses the description rather than refining it. An equation predicting infinity is not proof that infinity happened. It is proof that the equation reached the edge of what it was ever built to describe. What replaces that edge is still an open argument inside physics, and it deserves to be presented as one rather than settled with whichever answer sounds best for a single story. One serious proposal, growing directly out of the same mathematics that gives space a smallest indivisible unit of area and volume, suggests density simply cannot reach true infinity at all, because the geometry itself refuses to compress past a certain point, a maximum density set by the exact same combination of constants that produced the Planck scale in the first place. Instead of a singularity, this approach predicts a bounce, a contracting universe reaching that maximum possible density and rebounding outward into the expansion we are still living inside, with whatever came before the bounce sitting on the far side of a boundary current mathematics cannot see through cleanly. It is one candidate among several taken seriously by working physicists, not a finished answer, and naming it as anything more would be a disservice to everyone still working on it. None of the available proposals currently make a testable prediction sharp enough to settle the matter, which is precisely why none of them gets to be reported here as the answer. The fog that covers the smallest interval of time covers the universe's own first instant just as completely. It is the same fog, not a smaller, friendlier version of it reserved for laboratory conditions. The largest event physics has ever tried to describe, and the shortest interval physics has ever tried to define, turn out to be sitting behind the exact same wall of unresolved resolution. There is no flash of insight waiting on the other side, no story arriving fully formed once the right equation gets found. At the smallest gap inside a single neuron, inside the floor under a cooled quantum system, inside a crystal kept ticking on purpose in a freezer colder than the space between stars. The universe's first instant, and the gap between two neurons firing inside the body you are lying in right now turn out to be answering to the same unresolved question, separated by nothing but a staggering distance in scale, and by which one anybody has actually had the means to look at closely. That gap between two neurons is not empty, and what crosses it does not arrive as a stream. It arrives as a count. In the early 1950s, Bernard Katz and Paul Fatt were recording electrical activity at the junction between a nerve and a muscle in a frog, the classic preparation of the time precisely because the cells involved are large enough to thread a recording electrode into directly, expecting to study ordinary signals arriving from the brain. What they noticed instead was something nobody had asked them to look for: tiny, random electrical blips showing up in the muscle, even when no signal from the nerve was being sent at all, noise nobody else had bothered to look at closely. Katz and Fatt ruled that out the careful way, by changing the chemistry of the bath the tissue sat in rather than the wiring of the instrument. Lower the calcium available to the nerve terminal, and the spontaneous blips kept their exact same fixed size while becoming rarer. Raise it, and they grew more frequent without ever changing size. A wiring artifact would not have cared about calcium concentration in the surrounding fluid at all. A biological process built around discrete packets of chemical, released more or less often depending on calcium, would behave exactly the way the data did. That noise was not actually noise. Katz and Fatt measured the size of each spontaneous blip and found something almost nobody expected. They were not randomly sized at all. Every single one matched the same fixed amplitude, over and over, as if something inside the nerve terminal could only ever release its chemical signal in one fixed portion, never smaller, never a fraction of that portion, never anything in between. When an actual nerve impulse arrived and triggered a full response, the muscle's electrical reply came out as a whole number multiple of that exact same fixed unit, never a smooth, continuously variable amount. You can hear the shape of that result without needing to know any biology at all. A continuous flow can pour out any quantity you like, any fraction, any in-between value. A count cannot. Katz and Pfatt had stumbled onto a count, and what it was counting turned out to be one of the more elegant discoveries in the history of the nervous system. Electron microscopy later revealed exactly what was being counted. Inside every nerve terminal sit thousands of tiny membrane-bound sacs called synaptic vesicles, each one preloaded with a roughly fixed number of neurotransmitter molecules, somewhere in the range of a few thousand per sac, sealed and waiting. When a nerve impulse arrives, calcium floods into the terminal and triggers some number of these vesicles, never a fraction of one, to fuse with the outer membrane and dump their entire contents into the gap at once. One vesicle, one fixed packet, one quantum of signal. The size of the spontaneous blips Katz and Pfatt first noticed was the size of exactly one vesicle emptying on its own, by accident, with no impulse required to set it off. The calcium step itself turns out to be where the real randomness in this whole system actually lives. Whether any individual vesicle fuses on a given impulse is actually probabilistic, governed by how many calcium ions happen to arrive at exactly the right spot inside an interval measured in thousandths of a second. What is never uncertain is the size of each release once it happens. The system gambles on how many quanta get released. It never gambles on what one quantum actually weighs. That distinction, probability deciding the count while the unit itself stays fixed, is precisely the kind of structure a true quantum mechanism produces, and precisely the kind a smooth, continuous process never could. Katz received the Nobel Prize in 1970 for tracing that discovery all the way down to its mechanism, a recognition that the basic currency of communication between two neurons is not a continuous quantity at all. It is counted in whole, indivisible units. The same way a payment is counted in coins rather than poured out like water. The gap each vesicle empties into is itself only a few dozen nanometers wide, a distance neurotransmitter molecules cross by simple diffusion in a fraction of a millisecond, fast enough that the discreteness of the release never gets smeared out into something smoother by the time it reaches the far side. This is the same shape that the question of a true next step always comes down to: a smallest unit with nothing smaller sitting between it and zero, the kind of unit mathematics could never supply for a real number line no matter how the question was asked. A nerve terminal supplies one anyway, cleanly, for the structure of a thought crossing from one cell into the next. There is no half a vesicle. There is no in-between amount of neurotransmitter released. There is one quantum, then the next one, then the next, counted rather than poured. That same counting happens at every one of the roughly 100 trillion synapses threading through a single human brain, each one running its own small ledger of fused and unfused vesicles, all of it happening continuously and in parallel beneath any single thought a person manages to have. We do not get to feel any individual one of those countless small transactions. We only ever get to feel the accumulated result, smoothed into something that reads, from the inside, like a seamless stream of thought. Each vesicle that fuses is a single countable event, the same kind of true next step a neuron's refractory period already showed earlier, just one mechanism deeper, sitting at the actual chemical handoff between one cell's decision and the next cell's response. What I find remarkable about this particular discovery is how little fanfare it required. Katz and Pfatt were not chasing the foundations of discreteness in nature. They were doing careful, patient electrophysiology and refused to dismiss a small, strange signal as noise simply because nobody had asked them to explain it. The clearest confirmation yet that nature sometimes counts instead of flows came from two scientists paying close attention to something almost anyone else would have filtered out. You are not thinking in a smooth current right now. You are thinking in packets, vesicle by vesicle, synapse by synapse, an uncountable number of small, discrete, indivisible deliveries arriving in parallel across a brain that has never once needed your permission to work this way. We have now found this same shape, a count instead of a flow, sitting inside a crystal kept cold on purpose, inside the floor beneath a quantum system, inside a single firing neuron, and now inside the chemical handoff between any two of them. The question this leaves sitting open is not whether nature can count. It clearly can, at scales as intimate as the gap between two of your own cells. The question still standing is how far up that counting goes, and whether anything in you remains actually smooth once you look closely enough at it. Most descriptions of the observable universe stop at a boundary set by light that has already had time to reach us, a sphere a little over 46 billion light-years across, the largest distance any signal sent in the past has managed to cross. That boundary is not the one that matters here. A second, stricter boundary exists for the future, called the cosmic event horizon, and it answers a sharper question. If you sent a signal outward starting today, how far could it ever travel before the universe itself outran it? The answer is smaller than most people expect, and the reason is not the speed of light failing to be fast enough. Space itself is expanding, and that expansion is accelerating, driven by whatever physicists currently label dark energy for lack of a better name. Galaxies sitting beyond a certain distance, something on the order of 16 to 18 billion light-years away right now, are receding from us faster than light can close the gap between here and there. Send a beam of light toward one of them today, and the space between you and the beam stretches faster than the beam itself can cross it. The signal never arrives. Not because it was too slow, because the road kept getting longer underneath it. That is not a limit on instruments. A telescope with infinite resolution and infinite patience would still run into it, because the limit lives in the geometry of the expansion itself, not in anything built by human hands. Energy could not fix it. Time could not fix it either, because waiting longer only pushes more galaxies past the same boundary rather than bringing any of them closer. The galaxies sitting beyond that horizon right now are not gone from the sky immediately. Their old light, emitted long before they crossed the boundary, keeps arriving for an extremely long time, stretched and dimmed by the same expansion until it eventually fades past any detector's ability to register it at all. What ends, the moment a galaxy crosses the horizon, is the possibility of anything new ever reaching us from it again. We keep receiving its past. We lose all access to its future the instant the boundary is crossed, permanently, with no way for any future technology to reverse the loss. Run that same process forward far enough, and the implication gets stranger than most cosmology ever admits out loud. In a paper published in 2007, Lawrence Krauss and Robert Scherer worked out what an observer living tens of billions of years from now would actually be able to see. Every other galaxy outside our own immediate cluster will have crossed the horizon by then, their light redshifted into nothing detectable. The faint afterglow left over from the early universe, the signal cosmologists currently use to reconstruct the Big Bang itself, will have stretched past any wavelength a future telescope could register. A civilization arising in that era, doing careful, honest science with instruments far better than anything built today, would have no observational evidence that the universe expanded from a hot, dense state at all. They would see one galaxy, sitting alone in what looks like a static, eternal darkness, and every clue currently sitting in our own sky would already be gone. We are not living at the end of that process. We are living, by sheer accident of timing, near the beginning of it, in a universe young enough that the evidence for its own origin is still arriving. That is not a comfortable fact, and it deserves to be stated plainly rather than softened. The window for seeing what we can currently see is not permanent. It is a window, open right now, closing slowly enough that nobody alive will ever notice it shutting, and shutting all the same. There is a smaller, quieter version of the same problem sitting underneath even what we can observe today. Cosmologists call it cosmic variance. Every measurement of the universe's large-scale structure, its overall shape, its fundamental constants, comes from observing one single universe, one single roll of whatever process produced it. There is no second universe to compare against. No repeated trial to average over the way a laboratory experiment gets repeated 1,000 times to beat down its own statistical noise. The clearest place this shows up is in measurements of the cosmic microwave background, the faint relic glow left over from the early universe. At the largest scales that map can show, the ones spanning the biggest patches of sky, the uncertainty in what we measure never shrinks no matter how sensitive the detector gets, because we are not running out of resolution, we are running out of universe. There is only the one sky to look at, and a single sky only ever offers one data point for its own largest features. The cosmic variance problem is, in its own quiet way, stranger than the horizon itself. The horizon, at least, has a clean physical cause. Expansion, outrunning light. Something you could in principle calculate exactly if you knew the universe well enough. Cosmic variance has no fix even in principle. It is not a gap waiting for better instruments. It is the plain consequence of being a single observer embedded inside the one and only thing being measured, with no way to step outside it and compare notes. None of this is a reason to feel cheated by the timing of your own existence. It is closer to the opposite. Every piece of evidence gathered so far about the structure of the universe, the cosmic microwave background, the light from galaxies billions of years gone, the patterns that let inflation be tested at all, exists in a window that will not stay open forever, and was not guaranteed to be open at all. You happen to be reading these words during the only era in the entire future history of the universe when that evidence is still sitting in the sky, waiting to be looked at. That is not a small thing to have arrived in time for. Two different fogs, then, sitting at opposite ends of the same problem. One covers anything smaller than the Planck scale, a limit on resolution. The other covers anything beyond the cosmic horizon, a limit on access, made permanent and actively worsening by the same accelerating expansion that is, this very moment, carrying information past a boundary nobody gets to cross back over. Between those two fogs sits everything physics has ever actually managed to study, a narrow strip of accessible reality bounded on one side by what is too small to reach, and on the other by what is, slowly and forever, leaving. Inside that narrow strip, between a floor too small to see and a horizon too far to reach, is the one place this entire question was ever going to be answerable from. Not from outside the universe, looking in with infinite resources and infinite time. From inside it, with exactly the access available right now, asking what flow even means for something that was never given a complete view of anything, including itself. Return, quietly, to the room full of air described earlier, knowing only its temperature and pressure. Describe it statistically, and a flow gets generated automatically out of nothing but the gaps in what you know. Describe the same room completely, with nothing missing, and the flow disappears, because there was nothing incomplete left to generate it from. Neither description is wrong. Neither one is hiding a deeper truth the other one missed. The flow was never a property the room itself was holding, waiting to be measured correctly. It was a property of the relationship between the room and whatever was doing the describing. If that is the right way to think about it, the question of whether time is continuous or grainy, the one running underneath nearly everything covered so far, may be aimed at something that does not actually have a single answer waiting underneath it. Not because physics has failed to find that answer yet, because flow might not be the kind of thing that comes with one answer attached, independent of who or what is asking. A complete description, the kind that would erase any flow according to this same mathematics, has never once been available to anyone standing inside the universe rather than outside it. We do not get to choose our way out of that position. The cosmic horizon makes part of the universe permanently unreachable. Cosmic variance means even the part that is reachable only ever offers one example to learn from, never a second copy to check against. Completeness was never on the table for an embedded observer, not as a practical difficulty, but as a structural feature of being embedded at all. If flow requires incompleteness, and incompleteness turns out to be the one thing every observer inside this universe can never escape, then flow stops looking like an occasional accident of limited knowledge. It starts looking like the one condition nobody inside reality has ever been in a position to avoid. That is a strange thing to find sitting underneath everything covered so far. Instances of nature that count instead of flow. A crystal ticking on its own discrete schedule in a freezer colder than space. A neuron with a real physical floor under how fast it can fire again. All of that discreteness is completely real. Measured, confirmed, sitting in laboratories rather than arguments. And underneath all of it, mathematics built from a completely different direction says the very flow those discrete events are counted within might not be a fixed backdrop at all, but something generated locally, fresh, by whichever incomplete system happens to be doing the counting. Those two pictures are not fighting each other. A clock built from a granular, ticking process can sit comfortably inside a flow that is itself generated rather than supplied, the same way a struck bell can ring its own fixed note while standing inside a room whose acoustics were never fixed from outside either. Discreteness answers what a tick is made of. Thermal time answers where the flow those ticks are arranged inside actually comes from. Neither one needs the other to be wrong. There is something quietly settling about that. Once you stop expecting physics to hand over a single, final word. The universe was never obligated to resolve into one tidy answer, just because a question got asked carefully enough. Some of the deepest results gathered so far, the energy floor under change itself, the flow generated from incomplete knowledge, the discreteness showing up in cell after crystal, point in compatible directions without ever needing to merge into one clean sentence. That is not a failure of the search. It is closer to what an honest search actually looks like, once it has gone on long enough to stop expecting tidiness as a reward. You do not need any of this resolve to keep experiencing the thing it is trying to describe. The flow you are inside of right now, whatever its ultimate source turns out to be, a property of spacetime itself, or a property generated fresh by your own incomplete body describing its own incomplete self, is not waiting on a journal article to keep doing what it has always done. It is happening anyway, the same way it has been happening this entire time, with or without a settled answer underneath it. What is left, after everything gathered across so many separate, unrelated investigations, is not a conclusion. It is a single, quieter question, small enough to actually carry to sleep. Not what time is. What is generating the particular flow you are inside of, right now, in this exact room, in this exact body? and whether that question was ever going to have an answer that lived anywhere outside of you. There is an answer to that question sitting inside your own chest right now, and it does not require a journal article. It only requires noticing. Your heart is not humming along in a smooth current. It is firing, discreetly, once, then waiting, then firing again. A small cluster of cells near the top of it, generating one electrical discharge after another, each one separated from the last by a real, physical, non-negotiable gap. Somewhere between 60 and 100 times a minute, that gap opens and closes, and you feel none of the individual openings, only the accumulated rhythm they add up to. A second cluster of cells holds each signal for a fraction of a second before letting it continue. A deliberate pause built into the wiring on purpose, not a flaw, but the actual reason the upper and lower chambers manage to contract in the right order instead of together. A heartbeat is not a hum. It is a count with a real pause stitched directly into it that you have simply never needed to keep yourself. Your breath does something similar, slower, a rhythm generated by a small cluster of cells in your brainstem deciding, again and again, when the next inhale should begin, never a smooth current of air managing itself, always a fresh decision, made and remade, breath by separate breath, for as long as you have been alive without your ever once having to authorize a single one of them. And underneath both of those, in numbers too large to hold on to, something on the order of 100 trillion synapses across your skull are doing what synapses always do, releasing their chemical signal not as a stream but as a count, one vesicle, then the next, then the next. The same fixed packet, emptying again and again to carry the thought currently arriving at the end of this sentence into the part of you that just understood it. None of that needed permission from anyone outside you to be granular. None of it is waiting on physics to settle the question of whether reality is built from countable steps or something smoother. It already answered, quietly, every single second you have been alive, in a part of you too close and too constant to ever notice on your own. A crystal had to be cooled to within a hair of absolute zero, isolated, and tapped at exactly the right rhythm before it would show anyone this same stubborn, ticking refusal to blend into something smooth. Your body has been doing it at body temperature, surrounded by trillions of other cells, with no isolation and no help from anyone, every moment since before you can remember. And none of that counting feels like counting from the inside. It feels like one continuous you, one unbroken thread of attention moving from the first word of this sentence to the last. That feeling is real. It is also, as far as anyone has been able to work out, generated rather than supplied, manufactured locally by a body that was never given a complete account of itself and built a flow out of exactly that gap instead, the same way a struck string builds its own pitch out of nothing but its own tension. This is what it actually comes down to. Lying in the dark, breathing on a rhythm your brainstem decided without asking. Your heart counting out a beat you have never once had to keep track of yourself. You are not waiting for an answer to arrive from outside. You are sitting inside one, made of discrete, countable, indivisible events, threaded together by a flow your own body is quietly generating into something that feels, from where you are standing, like a single uninterrupted now. Count it if you want to, just for a moment, with no need to keep counting. One heartbeat. Then the gap. Then the next one. Notice how quickly counting dissolves back into simply feeling like time passing, the way it always has, the way it will again the moment your attention loosens and lets the count fold itself back into the flow that has been generating itself, beat by beat, breath by breath, vesicle by vesicle, inside you, this entire time, with no instructions from anywhere outside the room you are lying in. Thank you for staying with a question this large, all the way to a place this small and this close. I hope it follows you somewhere gentle from here. Sleep well.